Good day, everyone. Thanks for joining us for our webinar on AI on alternative cloud. I'm William Sigmund, Director of Sales Engineering with phoenixNAP. Special guest star today is Stryker, Director of Marketing Development at Solidigm.
Hey, everybody.
Couple of quick housekeeping things, just so you know, there's going to be a couple of poll questions. We very much encourage you to go ahead and answer the polls. It helps us tailor the presentation towards you. And you'll also notice in the interface, there are 4 handouts, 4 PDFs. Feel free to download those and peruse them at your discretion. First poll question is, what kind of IT infrastructure deployments are you using for your AI projects? We'll go ahead and wait for a few seconds for everybody to answer, and then go over those answers. All right, well, we see hybrid is gaining ground. That's not that shocking these days. All right, thanks for participating in the poll, guys. We've got one more quick question, and that is, what's your biggest obstacle for executing your AI strategy? Lots of all the aboves. That's interesting. Very good. Okay, let's go ahead and get started here. So here's what we're seeing out there. Obviously, AI is growing in popularity, right? There's no big shocker there. Storage has been a concern, and it's been a concern for our customers too. That's why we partnered up with Solidigm on this. Everybody we talk to, I think 96% is probably a low number. Everyone I talk to needs capacity, and they need it yesterday. Obviously, the growth is just insanely huge. Compute costs are going across the rails just because it's still hard to get equipment, as we all know, and power is becoming more and more of a concern for everyone. So just the cost driving behind that kind of hurt people to just build out their own. So let's talk about public cloud. And these are your traditional AWSs, your GCPs, that kind of thing. Yeah, they're great for deploying quickly, right? You can just drop a VM container up there, boom, 30 seconds later, you've got a VM container. Management's pretty easy because they do all the work for you. And of course, it's easy to scale. That's the big reason we all go to public cloud. The downsides, however, are vendor lock. Different vendors support different APIs, different ways to interact with their interfaces, all that stuff. The other thing to remember is you've got noisy neighbors, right? You're just a VM sitting out there on their compute. So you don't really have dedicated resources, obviously. So that can look a little spiky and lead to all kinds of inherent other problems. And then, of course, you have no visibility into the environment at all. So you don't know where it sits, what kind of equipment it sits on, what it's supposed to do versus what it is doing, et cetera, et cetera. So we propose alternative cloud. So the nice thing here is you don't have to provision ahead of time, right? Just like your public clouds, you can just take as you need. Obviously, again, as I mentioned before, we partnered with Solidigm because we need that high density NVMe storage and sometimes flash storage as well. The nice thing about using bare metal is you don't have the nosy neighbors. You have less security concerns. You've got your own dedicated networking, your own boxes, and you can focus more on security and reliability because you own the entire box. You're not just running a container out there in the nethers. With that, I'll hand it over to Ace, our guest star. Ace, it's on you, sir.
All right, thank you, Bill. Appreciate it. Hey, everybody. It's a privilege to be with you today. Thank you for joining us. Wanted to share a recent data point we came across, which is, I think, aligns well to the responses to the survey questions this morning. This is from a group called Digital Realty that publishes a global data insights survey on a periodic basis, and as the name suggests, interviews hundreds of folks globally about challenges around data. And so one of the questions that was asked in this survey in the most recent round, which was published for August of this year, was what's the biggest challenge your organization is facing to deploying your formal AI strategy? And there was a variety of responses, as you might expect, but interesting to see the #1 response across all the folks involved in the survey was lack of data storage, and that's it puts GPU power at #2, which is surprised me, to be honest. I sort of expected that's that when you go to you have conversations with customers, or we go to these conferences, and of course everybody's focused on the GPUs and the power consumption associated with these GPUs, and it's as it should be. But what we are seeing is the storage is a growing concern for a lot of enterprises out there. And that's because of, just the frankly astronomical amount of data that's used in training a lot of these frontier models, and even as an enterprise taking, a foundation model and doing fine tuning on top of it to sort of customize it for your specific use cases is demanding more and more data as these models become more capable and sophisticated. And so, of course, for a storage vendor like us, we like to see that that's something that folks are needing more of. But it does create challenges for us to continually develop increasingly dense and efficient storage solutions. And so we'll talk a little bit about that as well. I wanted to set the scene with this recent data point. Okay, so this is a couple of, every good AI presentation starts with charts that are showing up and to the right. I've learned that this year. I've been to a lot of events and had a lot of conversations, and it's almost always a line pointing up and to the right, whether you're talking about the size of models or the number of use cases or the number of parameters or whatever the case might be, investment in AI. These are the two that I want to focus on for the purposes of our conversation this morning. On the left, this is MIT data that talks about what I mentioned on our last slide, the median size of training data sets over time. If you followed the history of the recent history anyway of AI, you might be aware 2017 was kind of a watershed moment, right? That's when this famous white paper from some Google researchers came out, Attention is All You Need, introducing the concept of the transformer, and it kind of kicked off this current craze that we're in. And you can see that that was the moment on this chart where this kind of exponential growth in training data set size started. It was many times bigger in 21 than it was in 20. It multiplied again in 22 and again in 23. And this is we're talking about the data sets that are used, not the size of the model, not the parameters of the model. Those are all outcomes of the training process. We're talking here about an input into the AI model training process, which is the size of the data set itself. And so it can vary widely, obviously. If you're training a large language model, you may use something like the Common Crawl corpus, which is a collection of website scrapes over time, and that's up into the tens of petabytes now. It can get really big. If you're doing, image or video, it could get even bigger. And then, of course, there's lots of more sort of limited use, more, I'll call them economical models that are trained on smaller data sets. But as a trend, the median size is absolutely exploding, and we expect that to continue into when all is said and done for 24 and beyond. On the right-hand side is another piece of the storage puzzle, and frankly, what a lot of AI infrastructure specialists are worried about, is they start to think about how do we go out and how do we deploy these models and actually realize the business value of inference for whatever our industry is, whatever our use case is. There's all sorts of scary forecasts out there about energy consumption, right? I think the ARM CEO said earlier this year that he expects that by 2030, data centers globally will consume more power than the country of India, which is the most populous country on the planet. Just a couple of days ago, the AWS CEO came out and said that within a couple of generations, training a large language model will consume as much energy as a large city to train a single large language model. So, I mean, these are really wild, right? And this chart speaks to that a little bit. This is a US focused view, but we see this playing out all over the place. The numbers on the line that's sloping there up and to the right represent US data center energy consumption in absolute terms, in terms of terawatt hours. And then the little blue ovals on the bottom talk about that energy consumption as a proportion of total US power demand. So one way to read this is, hey, last year in 2023, data center consumption accounted for, less than 4% of overall U.S. power consumption. Within the next 5 years, it's going to more than double to 8% and beyond. And the slope of that thing indicates that if you were to, extrapolate out the next few bubbles, you could expect to see that number getting bigger and bigger. And so these are two things that we really think about. One, how do we deliver, storage devices and subsystems that help customers grapple with increasingly huge amounts of data? And two, how do we do it in a way that is energy efficient? Because it's not sustainable at the current pace, right? As these AI clusters demand more and more power, at some point we're going to hit a scalability ceiling where the cap on the rate of innovation is not going to be the great ideas people are having. It's going to be available power in the world. And frankly, we're already seeing that with some folks. Mark Zuckerberg's been in the news lately talking about, hey, we'd already be building out, more AI data centers if we could. Sam Altman was on a podcast recently. He said lots of things about AI are hard, but power is the hardest part. And so it's a big focus item for us, as well as a lot of other ecosystem members. This is a view of storage contribution to the power situation. As I mentioned, a lot of people worry about GPUs, and that's a very worthy thing to focus on. The current generation Hopper chips are quite power intensive, and as we look ahead at Blackwell and beyond, and others that are sort of entering the arena to try to compete with NVIDIA on the AI GPU front, we're seeing data center racks that used to be 4 to 6 kilowatts total power consumption up into the hundreds of kilowatts and potentially beyond with some of these new compute options that are coming online. But what we've observed, and this is actually observations from others as well, is that the storage can play a significant role in the overall power efficiency or lack thereof in an AI cluster. So the top one there from Meta and Stanford, I believe, they co-published a research paper, and they observed that in their data center, which was powered on the storage side mostly by a bunch of old hard drives, that their storage subsystem was consuming up to 35% of available power of the overall AI cluster. And in a more recent report from Microsoft and Carnegie Mellon, I believe, where they looked at emissions in particular, they noted that storage accounts for 1/3 of operational energy consumption in these AI data centers as well. So it is not all GPU. Storage can play a significant role in making poorly optimized choices for AI data storage can result in not just, impacts to performance, but also energy efficiency. The conclusion from the Microsoft and Carnegie Mellon paper, by the way, is there on the right, that the most direct way to improve the situation was make storage devices that can hold more, because all else being equal, of course, if your drives can hold more, you need fewer of them. That's less power, that's less cooling, that's less networking. And so it has a lot of implications as it plays out across the data center. This is some research that we've grabbed from a few publicly available sources. So when we talk about storage in an AI cluster, typically we're seeing it in two places. And we tend to call those, at Solidigm, we tend to call those direct attach and network attached storage. Direct attach is the stuff that goes into the GPU server. So if NVIDIA makes a DGX H100 box that's got 8 GPUs in it, typically has 8 U.2 slots where you can directly attach storage devices inside the box to your GPUs. And that tends to be where you want to put the really high performance, low latency stuff, the Gen 5 crazy throughput to keep your GPUs fed and highly utilized while you're doing a training run, for example. And then, in adjacent racks in a data centers where you see walls and walls of what we call the network attached storage. That's the storage servers and the JBODs or JBOFs, just a box of flash in the case of the NAND drives. And that's where the bulk storage is. And when we talk about these massive data sets that are being pulled into trained models, it lives there for the most part until it's needed by the GPU. And then there's a sort of a tiering where the data gets moved closer to the GPUs as it's needed. But when we look at just the network attached stuff and where the bulk of the data resides, one way to think about it that we see a lot of our customers using is a ratio between compute and storage. So for X amount of compute, how much storage do you need? What's the ratio that makes sense? And so what we're showing on this slide is per GPU rack, how much storage do we see hyperscalers and other customers using for some of their AI clusters. We're defining a GPU rack, by the way, as a rack with 4 of those GPU servers in it, 4 of those DGX units. And so it's a lot of compute, but there's a wide range in terms of how much storage folks are telling us they need for that unit of compute. On the smaller side, we've seen instances where it's a petabyte or less per GPU rack. And on the larger side, we've seen it go up into the dozens of petabytes per rack. And so there's a lot of drivers to this, and we expect to see, the trend to be more of those white dots on our line shifting to the right over time as these models become bigger, more capable. And so the drivers are kind of listed there across the bottom. There's the growth in the number, the amount of data, period. Multimodality means models that are dealing in multiple forms of information, not just text or not just images, but a multimodal model is one that can understand and generate outputs in a variety of different formats. We see folks moving to richer media. That large language to large video model transition is, of course, use case dependent. Not everything is going to become a video model, but we do see more and more models out there that are dealing in richer forms of media with much greater storage demands. Synthetic data is something that's been covered in the news quite a bit lately. This notion that you have a set amount of data that you've collected from your sources, whatever that might be, and you can actually then generate new data based on your original data that can be used to train the models or fine-tune the models or whatever the case might be. And for those, obviously, you've got to put the new data somewhere as well. So we see that as a driver. And then finally, data repatriation. So we see increasingly folks are worried, and I think the survey this morning reflected that folks are worried about data sovereignty. They want control over their data in an enterprise setting for security purposes, for privacy purposes, for retention, for compliance and audit purposes, whatever the case might be. And so those are some of the reasons that we see this network attached side of the storage world growing as time goes on, and continuing to sort of press the urgency of the efficiency situation because all this stuff consumes power, of course. This is an overview, and this is one that we could spend 20 minutes here, but I'm going to try to cover it in just a couple minutes for you. This is Solidigm's perspective of what we call the AI data pipeline. You may have seen other versions of this from other folks out there doing AI work. This is, we're not reinventing the wheel here, but what we are doing is trying to understand that there are discrete stages to the work that occurs in an AI workflow, and that associated with each of those stages, we can sort of characterize what's going on and make better storage decisions. And we can characterize that in a few different ways. We can look at what's the data magnitude, which is the top row of that table beneath. And we see it sort of starting really big, and as you pre-process your data and come up with you're cleaning it up, you're deduplicating, you're vectorizing your data in that data prep stage, the magnitude goes down, and then as you use that training data to train your model in the big middle section there, it goes down again, right? The model that comes out of these things might have started with hundreds of terabytes or even petabytes of raw data up front. The training data set might have been 1/10 that size, and then the model might be again 1/10 that size or 100th that size. Some of the bigger models that we're seeing deployed are still only in the hundreds of gigabytes or maybe low terabytes. So relative to the raw data up front, we're talking about a smaller amount. But then as you deploy and you go and you run inference and you're getting a bunch of new inputs and outputs, and you've got to put those somewhere, and maybe you're using them for fine tuning, or maybe you're connecting to some external data sources and using RAG to get better answers. All of that generates data, and then you've got an archive process at the end. And again, that data may be used for the next round of training to improve your model. It may be used, it may be held onto for compliance reasons. But we start to see the magnitude get big there again on the right-hand side and blow back up into the petabytes of data. Another way you can characterize these steps would be, what's the predominant I/O activity type? And that's what's in the second row of the table. That's not to say that this is the only I/O type that occurs at each stage. It's very much a mixed profile. But as we've studied this and characterized workloads that we've seen, we've observed trends broadly where, you know, writing a bunch of raw data to your object storage, to your network attached stuff, it tends to be a sequential write. As you're preparing that data and cleaning it up, as I mentioned, you end up with a lot less data than you start with in that stage. So you're reading more than you're writing. So it's a read dominant activity. Training itself in the middle tends to be heavily random read, 95% or more in our observations. And that's by design. You're showing these tokens, these bits of training information to your model in random order by design to avoid adversely affecting the weights and biases of your model. While training, you might be checkpointing as well to sort of save the state of your model in case you have a hardware failure or a software issue. You don't want to lose all your progress. Some of these training epochs can take, you know, weeks or even months for some of these frontier models, and so checkpointing is very important, and that's a sequential write activity. And it's important to do that one well and to have performance storage at that step, because when you're writing those checkpoints, your GPUs are generally sitting around and waiting for that to finish. They're not being fully utilized. And so that becomes a concern about GPU utilization if you've made kind of suboptimal data infrastructure choices at the checkpointing stage. And then across you can see the rest there. Inference tends to be random read. If you're talking about you know, some of the richer media types, again, it's a Gen AI model and you're creating videos or something, obviously the write activity is going to be proportionally greater. And then as you're writing all your inputs and outputs in the archive stage, that's a sequential write. And finally, another way to characterize it is, where is this work happening? We'll spend a lot of time on this one, but obviously there are instances where the whole data pipeline occurs in a core data center, where, you know, the work from training the model to deploying it and running inference never leaves, you know, the racks of the data center. And there are increasingly edge use cases where folks are wanting to move the infrastructure closer to the data sources and for reasons of latency or privacy or whatever the case might be. And so, especially in the second half of the pipeline here, we're seeing more of that work being done at the edge as time goes on. This is our bottom line message. You know, if you want to know kind of what's Solidym's point of view here, where do we stand? It's really about, hey, there's no AI without a whole bunch of data. That data requires smart infrastructure choices, including efficiency. That's you know, tends to be performance and efficiency, sort of the two primary drivers of optimization in infrastructure choices today. And our argument, of course, as a storage vendor, is, you know, we make the densest SSDs on the planet. We're very proud of that. We think we can, you know, we can save customers a lot of energy and rack space and TCO. And so that's our kind of our appeal to the customers is, hey, for the efficiency front, that's where we're really focused, and we're spending a lot of calories trying to get that right. So with that, thank you very much for your time and your attention. And Bill, I'll hand it back over to you.
Yep, and just a reminder, everybody, Ace will be hanging around for the Q&A. And I want to remind everybody, if you have questions, we are going to have a Q&A at the end, but feel free to use the chat option in there to go ahead and put your questions in there, and we'll answer them at the end. So what is bare metal cloud? That is software we're talking about here. Great for hybrid cloud, great for semi-public cloud. Basically, we built this thing cloud native from the ground up. It is, you own the server. You can orchestrate that server using all the tools you're used to today. So if you're using your Ansibles, your Terraforms, Pythons, anything like that, we have a rich API that allows you to spin them up, spin them down, install operating systems. Anything you'd normally expect in IT automation can happen right there. So as I kind of alluded to earlier, we already talked about the integrations, but the SDK is available on GitHub. Everything from Postman to GitHub Actions to, again, the aforementioned CI/CD stuff that we talked about. In addition to that, we want to beat this thing home. It is your server, right? So as you spin this thing up using automation or doing it in the portal, doesn't matter. It's your box. You're not sharing compute with anybody. You're not sharing storage with anybody. And you've got your own VLANs that are segregated from everybody else. Billing on it is much like you would expect with anything else. We do hourly, monthly, or annual. So if you just need to spin up and scale down, you can do that with the hourly option. Or if you want to hang on to it longer and save a little bit of money, you can bill it monthly or annual. And again, with the instant deployments, most instances from the second you click deploy server on the portal are up and running within 3 minutes. And that's, again, a full server, not just a container sitting somewhere. So we kind of talked about the billing already and the noisy neighbors, so I won't beat that up. Everything in the platform is the newest, latest, and greatest with Intel. We do offer the Intel Max 1100 GPUs. We do offer the 5th gen Xeon scalable processors, and Xeon 6 is coming. And then, of course, the flash drives that are local are Solidigm flash drives. Best part here is if what's on the box isn't enough, we also offer S3 compatible storage, as well as an all NVMe NFS type storage right there in the platform. So if you need to archive some stuff off to S3, you can do it right there from the same window. Or again, if you need some high-speed storage, you can just apportion it right there in the window as well. And again, as I mentioned before, the API modules, we integrate with Pulumi, Terraform, Ansible, and literally 20 others. For the old school coders out there, we also support Python as well. So use cases, startup projects, I see those a lot. So folks just want to, hey, let's try and make this piece of code, see what it does. I don't want to build out infrastructure for that. If it takes off, it takes off. I can scale it, not a problem. We also see a lot of folks going, hey, I need resources for about 3 months. I'm out of space in my data center. I need to work stuff out. So let me just put some of my workload over here in bare metal cloud. People that want different sites, facilities, and regions, we can offer it globally. If you go in the bare metal cloud portal, you'll notice we have 10 different locations today, and we are growing always. As Ace mentioned, we're seeing more workloads on the edge. So we're actually working with some of the cell tower manufacturers to put it in the cell towers themselves too. So you're going to see more edge compute coming from us in the future as well. And then, of course, as I mentioned before, we offer advanced networking in there, whether it be bring your own IP, use our IPs, bring your own BGP, use our BGP to advertise. It's all in there and accessible. And first and foremost, on the network side, you're definitely going to save money on bandwidth. The first 15 terabytes is free at every region. And then after that, it's literally fractions of a cent per gig. So you're going to save a ton of money compared with those public clouds. Now, as we talk more about this, these are built for AI workloads. The Solidigm NVMe drives we put in these servers are up to 8 times faster than SATA drives and more reliable for that matter. Those of you that are doing hybrid will be interested. We have AWS Direct Connect, Google Interconnect, as well as a direct connect to Microsoft Azure. And then, of course, we have Megaport in multiple sites as well. So if you wanted to build out your own mesh network using Megaport, you could do that, or connect it to any of those aforementioned public clouds as well. And of course, the whole point of this is to A, not be locked in with vendor lock, and B, you get more performance at a cheaper price. With that, we can go into the Q&A. And let me check the chat. Got a couple in the chat. Okay, hang on one sec. So the first question is, can you tell us a little bit more about the BMC portal? How is it easy to provision? You can literally provision a server in 6 mouse clicks on the portal. So you go in there, you pick what site you want, what box you want, what operating system you want, and then you tell it to roll the box. And then, like I said, literally 5 minutes later or less, that's up and running with your OS of choice. Which leads us into the second question. What OS can we run deployments with the Solidigm SSD? The answer is we support most Ubuntu flavors, and they're built in. Several flavors of CentOS, Elma Linux, Rocky Linux, Debian, Windows, ESXi, Proxmox, and Virtuoso. So for those of you that need to go ahead and virtualize things, we've got 3 different choices for virtualization as well. And the last one I'm seeing here is, which cloud model is optimal for scaling AI and data growth? Well, it really depends on the workload. What we're seeing and what we saw in the poll, frankly, and so you guys know, is most people are doing a hybrid cloud approach. I'll park some data somewhere, pull it down when I need it, work on it, send it back up, right? So yeah, this fits in very well with BMC. BMC is made to be part of that hybrid approach. As I said, you get that public hyperscaler kind of cloud look, but it's a private box. So all the tools you're used to using today, all the speed and efficiency you're used to today, all the scale out and scale down you're used to today is built in with this. And with that, one more poll. Would you like to get in touch with solution experts from phoenixNAP? We'll go ahead and let this poll sit for a second while you guys answer. Thanks, folks, for attending. We really appreciate your time, and you all have a great day. Thank you.
Thanks, everybody.